Hello, today we're going to do section 2.6, solving compound linear inequalities. Part 1, compound inequalities. Definition 1. A compound linear inequality combines two linear inequalities with an and or an or. For example, x plus 3 is greater than negative 4 and 4x minus 5 is less than or equal to 3. Next example, 2 times the quantity y plus 1 less than 0, or y minus 5 greater than or equal to 2. To solve a compound inequality, we find all values of the variable that make the compound inequality a true statement by using the same techniques we use to solve linear inequalities. We solve each inequality separately and then consider the two solutions. When solving a compound inequality with the word and, we are looking for all numbers that make both inequalities true. Our solution set will be the intersection of the two solution sets. Graphing each solution set can help us visualize where these sets overlap to give us the solution set of the compound linear inequalities. Solve 6x minus 3 less than 9 and 2x plus 9 greater than or equal to 3, following the steps outlined below. Step 1. Solve each inequality separately. So for the first one, we're going to add 3 to both sides, get 6x less than 12, and then divide by 6 and get x less than 2. For the second one, we're going to subtract 9 from both sides, get 2x greater than or equal to negative 6, and then divide by 2 and get x greater than or equal to negative 3. For step 2, we're going to graph the solution set of each inequality and determine where they overlap. So we had x less than 2, and we had x greater than, let me go up, or equal to negative 3. So I'm going to graph each of those separately on their own number line. So 2, let's just say it's right there, and I'm going to be less than 2, so that's an open circle, and to the left. Negative 3, let's say that's right here. That's going to be a filled circle because it's greater than or equal to, and then it's going to be to the right. Then the answer that we're looking for will be the overlap of these two graphs. And they overlap from 3 to 2. And then we're going to write the solution set of the compound inequality and interval notation. So in inequality notation, we can actually write it as a double inequality. So we get negative 3 less than or equal to x less than 2. That is inequality notation. Then in interval notation, it's bracket negative 3 comma 2 parenthesis. Example 3. Solve the following compound inequality, graph and write the solution in interval notation. So this one, I'm not giving you the steps. We're just going to go about it like we did before. So I'm going to solve them each separately. Now we have a choice here. We can distribute that 3, or my preferred step is to divide by 3. So then we get 2x plus 5 less than or equal to 6. Subtract 5. 2x less than or equal to 1. Divide by 2. Divide by 2. X less than or equal to 1/2. Move on to the second one. Again, we can distribute that 2, or we can divide by it. I'm going to divide by it. And then we get x minus 7 less than negative 3. Add 7, add 7. We get x is less than 4. Now I'm going to graph both of these separately. So less than or equal to 1/2. less than 4. And now, neither of those by themselves are our answer. Our final answer is going to be graphing them together. Now again, I'm only looking for where they overlap. Well, they only overlap from the 1/2 to negative infinity. So then we get x less than or equal to 1/2 or negative infinity to 1/2 bracket. So notice, if the arrows are going in the same direction, infinity will be part of your answer. When they're going in opposite directions, that's where it's going to be between the two values. Keep in mind, it is possible for the graphs never to overlap. In that sense, you will have no solution. Sometimes we have an and compound inequality that can be written more concisely. For example, a less than x and x less than b can be written simply as a less than x less than b, which we call a double inequality. The two forms are equivalent, which means a compound inequality with and may be presented as a double inequality. And I'll call that good for part 1 of section 2.6.